Okay, chat.
times 2 to the p minus 1, whenever this is prime.
Okay.
Now, because you're multiplying it by 2 to the p minus 1, which is even, this will always give an even number.
They can hear you right now.
Euclid had found a way to generate even perfect numbers, but he didn't prove that this was the only way. So there could be other ways to get perfect numbers, including potentially ones that are odd.
And that rule says
400 years later, the Greek philosopher Nicomachus published Introductio Arithmetica, the standard arithmetic text for the next 1,000 years. In it, he stated 5 conjectures, statements he believed to be true, but did not bother actually trying to prove. His conjectures were: 1. The nth perfect number has n digits. 2. All perfect numbers are even. 3. All perfect numbers end in 6 and 8 alternately. 4. Euclid's algorithm produces every even perfect number. And 5. There are infinitely many perfect numbers. For the next 1,000 years, no one could prove or disprove any of these conjectures, and they were considered facts.
You got an animal print maxi dress from JCPenney for $54, which means you also got a reason to use your standing desk for $54. We've got the receipts. Yes, JCPenney. Price includes 20% off coupon. Offer good through 9/6.
But in the 13th century, Egyptian mathematician Ibn Fallis published a list with 10 perfect numbers and their values of p. 3 of these perfect numbers turned out not to be perfect at all, but the remaining ones are. The 5th perfect number is 8 digits long, which disproves Nicomachus's first conjecture. And the next thing to notice is that both the 5th and 6th perfect number end in a 6, so that disproves Nicomachus's third conjecture, that all perfect numbers end in a 6 or 8 alternately. 2 conjectures were proven false, but what about the other 3? 2 centuries later, the problem reached Renaissance Europe. They rediscovered the 5th, 6th, and 7th perfect numbers. So far, every perfect number had Euclid's form, and the best way to find new ones was by finding the values of p that make 2 to the p minus 1 prime. So French polymath Marin Mersenne extensively studied numbers of this form. In 1644, he published his results in a book, including a list of 11 values of p for which he claimed they corresponded to primes. Numbers for which this is true are now called Mersenne primes. Of his list, the first 7 exponents of p do result in primes, and they correspond to the first 7 perfect numbers. But for some of the larger numbers, like 2 to the 67 minus 1, Mersenne admitted to not even checking if they were prime. To tell if a given number of 15 to 20 digits is prime or not, all time would not suffice for the test. Mersenne discussed the problem of perfect numbers with other luminaries of the time, including Pierre de Fermat and René Descartes. In 1638, Descartes wrote to Mersenne, "I think I can show that there are no even perfect numbers except those of Euclid."
He also believed that if an odd perfect number does exist, it must have a special form. It must be the product of a prime and the square of a different number. If he was right, these would easily have been the biggest breakthroughs on the problem since Euclid, 2,000 years earlier.
But Descartes couldn't prove either of those statements. Instead, he wrote, "As for me, I judge that one can find real odd perfect numbers. But whatever method you use, it takes a long time to look for these." Around 100 years later, at the St. Petersburg Academy, the Prussian mathematician Christian Goldbach met a 20-year-old math prodigy. The two stayed in touch, corresponding by mail. And in 1729, Goldbach introduced this young man to the work of Fermat. At first, he seemed indifferent, but after a little more prodding by Goldbach, he became passionate about number theory, and he spent the next 40 years working on different problems in the field. Among them was the problem of perfect numbers. This prodigy's name was Leonhard Euler. Euler picked up where Descartes had left off, but with more success. In doing so, he made 3 breakthroughs on this problem. First, in 1732, he discovered the 8th perfect number, which he had done by verifying that 2 to the 31 minus 1 is prime, just as Mersenne had predicted.
For his other 2 breakthroughs, he invented a new weapon, the sigma function. All this function does is it takes all the divisors of a number, including the number itself, and adds them up. So take any number, say 6. Sum up all its divisors and you get 12, which is twice the number we started with. And this will be true for all perfect numbers. The sigma function of a perfect number will always give twice the number itself, because the sigma function includes the number as one of its divisors. Now, this may seem like a small change, but it ends up being extremely powerful. So let's look at a few examples. Prime number, like 7. Now, because it's prime, you can't rearrange it into a rectangle. Therefore, the only divisors are 1 and the prime itself. So sigma 7 is 1 plus 7 is equal to 8. Now, to keep things easier to follow, we'll just stick to the numbers. But what if instead of 7, you had 7 cubed? Well, again, the sum of the divisors is really simple. It's just 1 plus 7 squared plus 7 cubed. Now let's use it on a different number, say 20. The sum of its divisors is 1 plus 2 plus 4 plus 5 plus 10 plus 20, which equals 42. But you can also write this as 1 plus 2 plus 4 times 1 plus 5. And this is what really makes the sigma function so powerful. If you have a number that is made up of other numbers that don't share factors with each other, then you can split up the sigma function into the sigma functions of the prime powers that make it up. So sigma of 2 squared times sigma 5 is equal to sigma 20. And since any number can be written as the product of prime powers, you can split up the sigma function of any composite number into the sigma functions of its prime powers. With his new function in hand, Euler achieved his second breakthrough and did what Descartes couldn't. He proved that every even perfect number has Euclid's form. This Euclid-Euler theorem solved a 1600-year-old problem and proved Nicomachus's fourth conjecture. Math historian William Dunham called it the greatest mathematical collaboration in history. But Euler wasn't finished yet. He also wanted to solve the problem of odd perfect numbers. So for his third breakthrough, he set out to prove Descartes' other statement, that every odd perfect number must have a specific form. Because if an odd perfect number does exist, you know two things. First, n is odd, and second, sigma of n equals 2n. Now, any number n you can write as a product of different prime numbers, and each prime can be to some power. So let's take that and put it into Euler's sigma function. So you get sigma of n equals sigma of all of those primes to their powers, which equals 2n. But since all of these factors are primes, you can actually split up the sigma function into the sigmas of the individual prime powers. Now, one thing to notice is that if you have a prime number raised to an odd power, for example 7 to the power of 1, then the sigma function will be even, because 1 plus 7 equals 8. You'll always get an even number because odd plus odd is even. If the prime number is instead raised to an even power, like 7 squared, then the sigma function returns an odd number. Sigma of 7 squared equals 1 plus 7 squared, which equals 57. Because odd plus odd equals odd. So if you have the sigma function of an odd prime raised to an odd power, it will give an even number. If instead it's raised to an even power, you get an odd number. And this is where Euler's genius insight comes in. Because here on the right side, you've got 2 times n, where n is an odd perfect number, and 2 is even. Well, what that means is that on the left side, there must only be one even number. Because if there were 2 even numbers, you could factor out 4. But that means you should also be able to factor out 4 on the right side, which you can't because n is odd, and there's only a single 2 here. So only one of these sigmas here can give an even number, which means that there is exactly one prime that is to an odd power, and all the others must be to an even power, just as Descartes had predicted. Now Euler refined the form a bit more and showed that an odd perfect number must satisfy this condition. But even Euler couldn't prove whether they existed or not. He wrote, "Whether there are any odd perfect numbers is a most difficult question." For the next 150 years, very little progress was made, and no new perfect numbers were discovered. English mathematician Peter Barlow wrote that Euler's 8th perfect number is the greatest that ever will be discovered.
For as they are merely curious without being useful, it is not likely that any person will ever attempt to find one beyond it. But Barlow was wrong.
Mathematicians kept pursuing these elusive perfect numbers.
And most started with Mersenne list of proposed primes. The next on his list was 2 to the 67 minus 1. So far, Mersenne had done an excellent job. He had included Euler's 8th perfect number while avoiding others, like 29, that turned out not to lead to a perfect number. But 230 years after Mersenne published his list, Eduard Lucas proved that 2 to the 67 minus 1 was not prime, although he was unable to find its factors. 27 years later, Frank Nelson Cole gave a talk to the American Mathematical Society. Without saying a word, he walked to one side of the blackboard and wrote down 2 to the 67 minus 1 equals 147 quintillion, 573 quadrillion, 952 trillion, 589 billion, 676 million, 412,927. He then walked to the other side of the blackboard and multiplied 193,707,721 times 761,838,257,287, giving the same answer. He sat down without saying a word, and the audience erupted in applause. He later admitted it took him 3 years working on Sundays to solve this. A modern computer could solve this in less than a second.
From 500 BC until 1952, people had discovered just 12 Mersenne primes, and therefore only 12 perfect numbers. The main difficulty was checking whether large Mersenne numbers were actually prime.
But in 1952, American mathematician Raphael Robinson wrote a computer program to perform this task, and he ran it on the fastest computer at the time, the SWAC. Within 10 months, he found the next 5 Mersenne primes, and so corresponding perfect numbers. And over the next 50 years, new Mersenne primes were discovered in rapid succession, all using computers.
The largest Mersenne prime at the end of 1952 was 2 to the power of 2,281 minus 1, which is 687 digits long. By the end of 1994, the largest Mersenne prime was 2 to the power of 859,433 minus 1, which is 258,716 digits long. Since these numbers were getting so astronomically large, the task of finding new Mersenne primes became more and more difficult, even for supercomputers.
So, in 1996, computer scientist George Woltman launched the Great Internet Mersenne Prime Search, or GIMPS. GIMPS distributes the work over many computers, allowing anyone to volunteer their computer power to help search for Mersenne primes. The project has been highly successful so far. We discovered 17 new Mersenne primes, 15 of which were the largest known primes at that time.
And the best part? If your computer discovers a new Mersenne prime, you'll be listed as its discoverer, adding yourself to a list that includes some of the best mathematicians of all time.
There's even a $250,000 prize for the first billion-digit prime. In 2017, church deacon John Pace discovered the 50th Mersenne prime by using GIMPS. The number, 2 to the 77,232,917 minus 1, is more than 23 million digits long, and it was also the largest known prime at the time.
To celebrate this achievement, the Japanese publishing house Nanai Rosha published this book, The Largest Prime Number of 2017. And all it is that number spread over 719 glorious pages. It's wild. The size of this font is so tiny. The book quickly rose to the #1 spot on Amazon and sold out in 4 days. A year later, the 51st Mersenne prime was discovered. It's 2 to the 82,589,933 minus 1. And this number has 24,862,048 digits. But there's something I enjoy about the absurdity. Like, there is knowledge in here, but it's not the kind of knowledge that anyone's ever going to read out of a book. But in some way, it's nice that there's this physical artifact that like has the number. If ever we lost all the prime numbers, you know, someone could find this book and be like, Here's a big one. As of today, this is still the largest known prime. And since numbers of this form grow so rapidly, the largest Mersenne prime is almost always the largest known prime. Computers have been incredibly successful at finding new Mersenne primes and their corresponding perfect numbers. But we've still only found 51 so far. So you might suspect that there are only a finite number of them, which would mean that Nicomachus's fifth conjecture would be false, that there aren't infinitely many perfect numbers.
But that might not be the case. The Lenstra-Pomerantz-Wagstaff conjecture predicts how many Mersenne primes should appear based on how large P is. Now, this is the actual data. The conjecture performs remarkably well, but more importantly, it predicts that there are infinitely many Mersenne primes, and so infinitely many even perfect numbers. The Mersenne primes are just so large and rare that they take a lot of time and computer resources to find.
But a conjecture is not a proof, and up until this day, this problem shares the title of oldest unsolved problem in math with the other open problem: do any odd perfect numbers exist?
The easiest way to solve this problem is by finding an example. So maybe we could just check different odd numbers and see if one of them is perfect.
That's exactly what researchers tried in 1991. By using a smart algorithm called a factor chain, they were able to show that if an odd perfect number does exist, it must be larger than 10 to the power of 300.
21 years later, Pascal Occam and Michael Rao raised that lower bound to 10 to the 1,500, with recent progress pushing that number up to 10 to the 2,200.
With numbers that large, it's unlikely that a computer will find one anytime soon. So we'll need to get smart.
What would a proof look like? Like, how could we actually prove this?
I think the main idea that people have been trying to approach this problem with is coming up with more and more conditions odd perfect numbers have to satisfy. It's called this web of conditions, where it has to have 10 prime factors now that we know, and maybe thousands of non-distinct prime factors, and it has to be bigger than 10 to the 3,000, and it has to do all these different things. And we hope that eventually there's just so many conditions they constrain the numbers so much that they can't exist.
Since Euler, mathematicians have kept adding new conditions to this web.
But so far it hasn't worked.
But there might be another path.
When Descartes was looking for odd perfect numbers, he came across 198,585,576,189, which you can factor as 3 squared times 7 squared times 11 squared times 13 squared times 22,021. Put this into Euler's sigma function, and you find it is equal to 2 times the original number. In other words, it is perfect. That is, if 22,021 were prime. But it's not, because it is equal to 19 squared times 61. And filling that in shows that it is not perfect. Numbers like this, that are very close to being odd perfect numbers, are called spoofs. Spoofs are a larger group of numbers. So odd perfect numbers share all properties of spoofs and then a few extra ones. And the goal is to find properties of spoofs that ultimately prevent them from being odd perfect numbers. For example, one condition of odd perfect numbers is that they can't be divided by 105. So if you find that spoofs must be divisible by 105, then this would prove that odd perfect numbers can't exist.
In 2022, Pace Nielsen and a team at BYU found 21 spoof numbers, including Descartes' number. And while they discovered some new properties of spoofs, they didn't find any that rule out odd perfect numbers.
So how large would an odd perfect number have to be?
They don't exist.
You don't think odd perfect numbers exist?
No, they don't exist. I wish they did. That'd be really cool if there was this one gigantic odd perfect number out in the universe. They don't exist. No.
How are you convinced that they don't exist?
There's something called a heuristic argument. It's not a proof, so if we had a proof, we'd be done. It's just an argument from, okay, we think primes occur this often of this type, and you put those pieces of information together and you think, okay, on average, how many numbers should be perfect?
This argument, which was made by Karl Pomerantz, predicts that between 10 to the 2200 and infinity, there are no more than 10 to the negative 540 perfect numbers of the form n equals pm squared.
With odd perfect numbers, the heuristic says we shouldn't expect any. We've searched high enough now that we think we have enough evidence they shouldn't exist anymore.
My understanding is this heuristic argument, it also predicts that there are no large perfect numbers, even or odd. So
That's true. So there's a downside to this. Yeah, there's a downside because it says there shouldn't be large, even perfect numbers, and we actually expect there to be infinitely many. And so, okay, so why do I believe the heuristic in this case and not this case? You're right. Am I being hypocritical about that? There are other aspects you can add on to the heuristic and make it stronger. Let me put it that way. But you're right, it's not a proof.
for now, this is still the oldest unsolved problem in math. Euler was right when he said, whether there are any odd perfect numbers is a most difficult question. So are there any applications of this problem?
I can say no.
Now, many people may think that if there are no applications to the real world, then there's no point studying it. Why should anyone care about some old unsolved problem? But I think that's the wrong approach. For more than 2,000 years, number theory had no real-world applications. It was just mathematicians following their curiosity and solving problems they found interesting, proving one result after another and building a foundation of useless mathematics. But then in the 20th century, we realized that we could take this foundation and base our cryptography on it. This is what protects everything from text messages to government secrets.
Whenever you have a group of people put their minds towards a problem, something good's going to come out of it. If it's only at the beginning, this doesn't work. Okay, well, as Edison said, I learned 999 ways of not making a light bulb. Eventually, I got a good way to do it. It's the same with math. You have a problem and you throw your mind at it, and others do too, and you come up with new ideas, and eventually something good comes from that process.
Einstein's general relativity was built on non-Euclidean geometries. Geometries that were developed as intellectual curiosities without foresight of how they would one day change the way we understand the universe. How many people do you think are working on the problem of perfect numbers right now?
I guess around 10 people currently have papers in the area, 10 to 15. If you're a high schooler and you just love mathematics and you think, I want a problem to think about, this one's a great problem to think about, and you can make progress, you can figure out new things. Yeah, don't be scared. Hundreds of people have thought about this problem for thousands of years. What can I do? You can do something.
Why should you do math if you don't know that it will lead anywhere? Well, because doing the math is the only way to know for sure. You can't tell in advance what the outcome will be. Like, this problem might turn out to be a dud. We might solve it and it might not mean anything to anyone. Or it could turn out to be remarkably helpful. The only way to know for sure is to try.
Now, it's more likely, okay, 42 is the...
In today's world, it often feels like you've got to choose between following your curiosity and building real skills you can apply. But the truth is, it's essential to do both. Fortunately, there's one learning platform which allows you to do just that, and it's this video's sponsor, Brilliant. Brilliant will make you a better thinker and problem solver by helping you build real skills in everything from math and data science to programming, technology, you name it. Brilliant has thousands of lessons for you to explore, so you can follow your curiosity wherever it leads you. And you won't just learn key concepts, you'll actually apply that knowledge to real-world situations, giving you real hands-on intuition. With Brilliant, you can learn by trying things out for yourself. That's what makes learning with Brilliant just so powerful. And along the way, you can set goals, track your progress, and level up with guided learning paths that let you go deep into specific topics. I think that learning something new every day is one of the best gifts you can give yourself, and Brilliant is the perfect way to do it, with bite-sized lessons that you can do right from your phone. So even if you only have a few minutes, you can feed your curiosity, sharpen your mind, and build new skills. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/Veritasium. Scan this QR code or click the link in the description. And the first 200 of you will get 20% off Brilliant's annual premium subscription. So I want to thank Brilliant for sponsoring this video, and I want to thank you for watching.
For the past year, I've been asking myself, how do you define a smooth path? It's an innocent question that seems straightforward at first. After all, we've used paths throughout history, both in the real world and in my field of game development. But it turns out, this goes much deeper than one might expect. What do we mean by path? And for that matter, what do we mean by smooth? I was propelled into a year-long journey, filled with twists and turns, unexpected realizations and discoveries, making connections to things I hadn't thought of before. I was knee-deep in research and math papers. I wrote pages and pages of notes. Eventually I got to the point of finding errors in numerous resources online, and then I got burnt out. But I have finally reached the destination of my journey, and this is where yours will begin. I'm so happy to finally share with you the culmination of that year-long deep dive into the continuity of splines.
You got the pie sheet so I can do practice?
Do I do what?
Do you have the pie circle sheet so I can do practice?
In the virtual worlds we create, there's often a need to define paths. These can take many different forms, such as this conveyor belt in Satisfactory, or this more complex type of path that you see in this roller coaster, using a path not only for position, but for rotation as well. We also use paths in 2D games to animate things like this in a smooth manner. In fact, almost all animations in games have a type of path defined for every single joint in a character's body. Your browser has paths defined for every letter in every word you read. Even in art tools, we sometimes use something called a gradient map. This too is a type of path where the input is luminosity instead of time, and the output is in color space. Now, these might seem pretty unrelated. These are wildly different concepts from all over the digital world, but there's something they all have in common. All of them are splines. And this journey starts with Bezier curves. The most basic way to create a path between 2 points is to simply draw a straight line between them. We can then blend these 2 points to find any point in between. The input to this function is a percentage, or a t-value, a value from 0 to 1 that determines how far we want to go from the first point to the second. This is the most common type of blending function known as lerp, or linear interpolation. Mathematically, we can define lerp as a function that takes a single value, our t-value from 0 to 1, and uses that to blend between the first 2 points, where 0 gives you the first point and 1 gives you the end point. But usually, when we create a path, we want to be able to create smooth curves, not just straight lines. So what if we add another point? We now have 3, and between them, 2 lines. We can then use the exact same lerp function to blend between these points on each line. But what if we then connect these 2 points? We now have a 3rd line between the interpolated points, and let's try using lerp on that line as well. Now watch what happens to this point as we change t from 0 to 1. This is the magic of Bezier curves. Using only linear interpolation, we end up with a smooth curve. This one in particular is a quadratic Bezier curve. Of course, we don't have to stop here. We can add another point, lerp on those lines, connect those points, lerp on those lines, connect those 2 points, and finally lerp on the last line. And again, this will trace out this beautifully smooth path. This one has 1 more point and is of 1 degree higher, meaning this is the cubic Bezier curve. The cubic Bezier is by far the most common curve. Almost every font and vector graphics tool is using the cubic Bezier, and so it's worth digging deeper into how it works. So let's write all this down. We have 4 points, P0 through P3. We then get these intermediate points before the final point that we get out of the function. This method of recursively lerping between our points is called de Castillo's algorithm. It's very popular and incredibly easy to remember. You just lerp until you run out of things to lerp. It's also very numerically stable, but it can sometimes be a little expensive to calculate. Let's look at the same math, but from a different perspective. If we write all these lerps out as a math function, we can shuffle things around and express them as a factor of each point. This is called the Bernstein form of Bezier curves. A geometric interpretation of this is taking the vectors that represent each point, scaling each of them by their own cubic polynomial, and adding them all up. These polynomials might seem like they came out of nowhere, but this is just what you get when rearranging the lerp math to be expressed as a factor of each point. These polynomials act as influences of each control point. So in the beginning, the first point has all influence. This is then slowly shifted over until the last point has all the influence. This is a special type of weighted sum called a convex combination, as these polynomials add up to 1 for all values of t. A third interpretation I'd like to show is particularly interesting because it allows us to write more optimized code. Instead of writing them as factors of points, what if we rearrange them as factors of powers of t? As you can see, we have a constant factor t, t squared, and t cubed. The reason this is computationally efficient is that we can cache these coefficients for each arrangement of the control points. Now, a geometric interpretation of this one is a little harder to wrap your head around. It's definitely not as intuitive as the others. But we can think of it as 4 vectors that are each scaled by specific powers of t. We have a constant p0 plus a vector scaled by t plus a vector scaled by t squared plus a vector scaled by t cubed. And so even though all 3 of these are describing the exact same curve mathematically, they have different geometric interpretations and performance characteristics. There's one last way we can rearrange this math that is by far my favorite: the matrix form. One thing I particularly like about it is that it separates out all the magic numbers. It lets us see patterns and symmetries that were otherwise hard to spot. This is called the characteristic matrix of the cubic Bezier curve. Now, this matrix form actually encapsulates both the Bernstein and the polynomial interpretation. If we multiply the powers of t by the characteristic matrix, we get the Bernstein polynomials. If we instead multiply the characteristic matrix by the point matrix, we get the polynomial coefficients. But a cubic Bezier curve doesn't get us very far. What if we want to create a longer, more complicated path? Luckily, Bezier is generalized to any number of points. For this set of control points, we're doing the exact same thing as before. Lerp until there are no more things to lerp, and we're left with 1 point tracing out the path. Not that anyone would call it this, but technically this would be a dodecic Bezier curve. Just like the cubic Bezier, we can describe the influence of each point with its Bernstein basis polynomials. As you can see, the same principle applies. It starts out with the first point having full influence, and then it will ride the waves through the middle until the last point gets full influence. But if we want to use this for paths in games, we now have a problem. Let's say we want to use this path to define a road from one town to another. If we focus on a single control point, you can see its influence is actually across the entire curve, which in practice means that if we move this point around, the entire curve will actually change shape. And this is a huge problem if we want to create precise and intricate shapes snaking around mountain ranges or whatever else might be in the way of our road. In other words, we have no local control. Every movement of every point affects the entire curve. In addition, it doesn't actually pass through most points, making it very difficult to make specific paths of the shape you want. And finally, given the sheer number of control points, it'll either be numerically unstable or very expensive to calculate. Clearly, higher degree Bezier curves are not the answer. We need to dive deeper to find a better way, a way to control shapes without affecting every single other point in the curve. And perhaps we left our cubic Bezier curve a little too early. Maybe they were just feeling a little lonely. Perhaps they just needed some friends to realize their full potential, to work as a team and achieve what they couldn't do on their own. And together, they formed the Bezier spline. Instead of having just one segment, we now have multiple Bezier curves joined together, sharing endpoints. Traversing this path requires some extra work though. The input t value was traditionally from 0 to 1, acting as a kind of percentage along the curve.
So right now, it's like a temporary president.
But in this case, our parameter range has to extend across all curves.
He's just trying to...
If you look at the full input range, we can easily map each curve to each whole number. So let's define a u value, the input parameter for the whole spline. The integer part can then represent the curve index, and the fractional part the local t value for each individual curve. And so now we've defined a simple method to create, shape, and move along a set of Bezier curves. This is now getting a little more complex, so let's make sure we're on the same page about what all of these elements are called. The input u value is in a one-dimensional space called parameter space. The points we define are called control points. A spline then generates individual curves based on those control points, where each curve is effectively using its own math function. These curves meet end-to-end at points called joins or knots. Note that in this case, the joins happen to also lie on control points, but this is not always the case. Each curve is then assigned an interval in the input parameter space that helps us associate any given input u value to a curve. The values here are called knot values, and the distance between them knot intervals. In this video, we'll be focusing on uniform splines, where all of our knot intervals have the same length. In this case, a length of 1, making it very easy to map each curve to the unit interval of 0 to 1. Non-uniform splines where the knot interval varies are significantly more complicated, so let's save that for a future video. Now, we wanted to use this to create a road from one town to another, but we struggled to get it to work with a single curve because we didn't have local control, among other things. So, has our spline fixed these problems? Well, if we map the basis functions into our parameter space, we can analyze the weights to see if we now have local control. If you look at the influence of this control point, it lies entirely within the span of the third curve. What this means is that if we move this control points, only that span will be affected, leaving the rest of the spline completely unchanged. If we look at this point, you can see that its influence is twice as large, which makes sense as two curves share this point. But it still doesn't span further than these two curve segments, and so we still have local control, again leaving the rest of the spline unchanged. So with the cubic Bezier spline, we've regained local control. Not only that, but because we're using cubic Beziers, it doesn't actually get any more expensive by adding more points. We're effectively just sampling one cubic Bezier, even though the path is much longer and more complex.
You're just counted as half a citizen because you're marrying a town.
So compared to the higher degree Bezier curve, it's cheap. Finally, if we look back at our original set of control points, we don't just pass through the start and the end anymore. We now pass through every third point, which means it's significantly easier to create whatever shape you want. In other words, it's now interpolating every third point. It's really no wonder why the cubic Bezier spline has become so loved. It really gives you a huge amount of control. You can make pretty accurate circles with it, though not actual circles. You can be a little cheeky and place the middle 2 points exactly third way to make linear segments. It's the spline used when doing vector graphics, especially in font rendering or Photoshop's pen tool. The key to the undeniable flexibility of the Bezier spline lies in the arrangement of the 2 control points next to the curved joins, sometimes called the tangent points. They have 3 common configurations, all with different properties. One is the split tangents that you can use to make sharp corners, also known as broken tangents. The second one is where you align the 3 points around the curved join. This ensures the 2 curves are tangent with each other at that join. Finally, you can also mirror the tangent points around the join, making them not only aligned, but also the same distance from their shared control point. With all these tools in mind, we can now easily create paths and animate objects on it, right? Although, something seems wrong. Look at how they move across the curved joints, especially this one. It seems to suddenly change velocity. And so, this is where we need to talk about a concept called continuity. Continuity is a measure of how connected the curves are. As you can see, these curves are connected. These curves meet at the joins, and so we can give this a name. This spline is C0 continuous. If we separate these curves, it's no longer continuous at all, and so it's no longer C0 continuous either. So what continuity means is that position changes continuously. There's no sudden jump or discontinuity in this path. But we noticed something was wrong with the way our cubes were moving across joins. They appear to make little jumps in speed. And anytime you want to analyze change, it's worth looking into derivatives. Remember the matrix form of the cubic Bezier? One very nice feature of this form is that calculating the derivative is trivially easy. All we need to do is differentiate the powers of T matrix using the power rule. Now, this might seem a little abstract. What is the derivative of a curve in 2D space? Well, a more common name for the first derivative of position with respect to time is velocity. The second derivative is called acceleration. The third is called the lesser-known jolt. Now that we know how to calculate the velocity, let's visualize and see how it behaves in this path. Did you notice how it jumps at every join? The length changes, in other words. There's a discontinuity in speed. We can make this even more explicit by drawing the graph of the velocity. Notice what happens at every join.
But they're just shut up and they don't. So because the government is giving them whatever they need.
The velocity graph is discontinuous. It's disconnected at every join. So even though we aligned our tangents, there's a sudden change in speed. Now watch what happens to the velocity graph if we make these tangent points mirrored instead of just aligned.
You know why?
America is also a good friend with Saudi Arabia.
The velocity around the curve is now continuous. There's no sudden jump anywhere anymore. This curve is now C1 continuous because both its position and its first derivative, velocity, is continuous. Now, for continuity to be valid, all the previous derivatives have to be continuous too. Every C1 continuous path is also C0 continuous. If we disconnect these curves in position, it's neither C0 or C1 continuous anymore, even though the velocity is still continuous in and of itself. The discontinuity in position prevents it from being classified under any continuity class. But why does mirroring the tangent points make it C1 continuous? This is where looking at the algebra is helpful. First, let's label our point. Now, C0 continuity is trivial. These two curves share the point P3, and so that's already done. C1 continuity seems to happen when the tangent points are mirrored. Notice how when we move them, the velocity becomes discontinuous. So to write this algebraically, this is the condition that has to be met. The velocity at the end of curve A, where the input t-value is 1, has to be equal to the velocity at the start of curve B, where the input t-value is 0. You can plug in the equation here for the Bezier curve and solve for P4. I'll spare you all the algebra, but this is what you end up with, which is what we would expect. P4 is now equal to P2 reflected around P3. In other words, it's mirrored. Now, I've made P4 grayed out, as we've actually lost a little bit of control now if we want this join to have C1 continuity, because P4 is now fully determined by P2 and P3. But it's a little sacrifice we're willing to make. Notice how the velocity stays continuous no matter where we move P2. One would hope that C1 continuity could fix all of our issues with animation. We've clearly improved it by removing that velocity discontinuity, but there's still a more subtle thing going on. Let's take a closer look. Can you see how the boxes suddenly and harshly start turning in the other direction here? The only way for something to change direction is through acceleration. So let's investigate how it changes across the spline. We can already see that we have another discontinuity. It makes a huge jump at the join. As you can see in the graph, it's discontinuous. So let's write our acceleration continuity constraint explicitly. For C2 continuity, the acceleration at the end of curve A has to equal the acceleration at the start of curve B. Skipping all the intermediate steps, this is what we end up with. Geometrically, we can interpret this as P5 should be placed at the vector from P2 to P3, originating from P1, multiplied by 4. P5 is now fully constrained by P1, P2, and P3. If you're familiar with constraints, you might have already spotted a problem. But this works. If we change the shape of the first curve, the position, velocity, and acceleration are all continuous. So we successfully joined Béziers with C2 continuity. Or did we? Something very bad is about to happen. Here's what's up. We've been talking about ensuring continuity around the join at P3. But in order for us to make the entire spline C2 continuous, we need to also apply these continuity constraints around the other joins. So P5 will now determine the position of P7 because, again, mirrored tangents for C1. The same applies to P10. For C2 continuity, P4, P5, and P6 now control the position of P8. And P8, P9, and P7 controls the position of P11. We don't seem to have a lot left to control, do we? Now watch what happens if we move a single point, even just a tiny bit.
They're making all these problems in the Middle East. The Middle East, they just want Israel.
As you can see, it yeets off to fucking wherever, making it absolutely useless as a spline.
It's the hand that they have in there.
But it's very, very smooth. Look at how smooth this movement is. At least, personally, as someone who's spent staring at these things for a year, there's something mesmerizing about C2 continuity.
I mean, the whole problem that happened, like,
And let's also look at the acceleration.
everyone thought, like,
But this actually has grave implications for cubic Béziers. In other words, you can't make a cubic Bézier C2 continuous. It is literally impossible without losing local control. And having that control is the whole point of using splines in the first place. Our beloved cubic Bézier has betrayed us. It was so useful for creating shapes, but now we've discovered this huge flaw in its construction. But because we're all curious cats, we have to ask ourselves, what happens if we go to C3 continuity? And so, same thing here, the third derivative at the end of curve A has to match the third derivative at the start of curve B. This is now getting significantly more messy. The geometric interpretation is almost useless at this point, but We're basically taking the vector from P0 to P3, adding it to P3, then we take the vector from P2 to P3 and from P2 to P1, add those two together, add it to the first vector, and multiply it by 6. Long story short, the position of P6 is now determined by P0, P1, P2, and P3. Our problem of losing local control has now reached its worst case. We don't have control over P9 anymore, and the same goes for P12. The curve is now even more sensitive to the initial conditions. A tiny movement of a control point in the first curve will massively throw the rest of the spline around. In fact, we've lost so much control that this can't even be called a spline anymore. It's actually equivalent to simply extrapolating the first curve by increasing our t-value beyond 1. And since this is now just one curve, not only is it C3 continuous, it's actually C infinity, because there are no joins anymore. All derivatives are connected. To summarize, in a cubic Bezier, when the tangent points are mirrored, we have C1 continuity. When we have a broken join, the velocity is no longer continuous, so it's only C0 continuous. When the curve is entirely disconnected, there's no continuity at all. An important thing to remember, what we've been focusing on is the continuity at the join between curves, because every other point on the curve is C infinity, as they use the same function. For a more formal definition, two functions a and b are Cn continuous if the 0th through the nth derivative are all equal at the join. This is called parametric continuity. Continuity is absolutely central to the discussion of splines, and it's actually the primary motivator for investigating multiple different types of splines. But we're not quite done yet with continuity, because there's a different type of continuity lurking in the shadows. So we now know mirrored tangent points are C1. Alright, broken tangent points are C0. But what about aligned tangent points? Clearly, there's some kind of continuity we care about here, even if it has a sudden speed change. If we're using these for vector graphics, we don't really care about speed. We only care about the shape it creates in the end. This is exactly what geometric continuity is all about. When we look at the velocity, sure, it might have this sudden jump in length, which in this case is a change in speed, but again, what if we don't care about speed? What if we only care about the shape? To analyze this, we can get the tangent vector by simply normalizing the velocity vector. In other words, forcing it to have a length of 1. Let's also throw in the normal vector, because it's trivial to calculate in 2D, and it helps us visualize this a little better. Now, this is perfectly continuous, right? The change in speed has literally no effect on our tangent and normal. This is called tangent continuity, and we're going to call this G1. At this point, you probably know where this is going, right? That 1 next to the G is practically begging us to investigate, what is G2? This is not just a mathematical curiosity. G2 continuity is actually crucial in industrial design, especially for shiny things like car bodies or phones. And perhaps a little sneakily, the shape of the Apple app icon. In order for us to analyze this, we're going to have to enter the third dimension and turn on the lights. What we've got here is a perfectly reflective surface, which will help us analyze the geometry. If we look closely, we can see that something is wrong here. Our tangents are perfectly aligned, and yet somehow there's a seam in our reflection. Isn't it enough to just align the tangents? Well, clearly it's not. And if we change the background to these dots, it's made even more clear just how discontinuous this is. This doesn't just apply to Bezier curves. A perhaps unexpected place where this problem occurs is when you join circular arcs to flat segments. Here too, we see this extremely sharp discontinuity at the seam. And again, the dots will make an even stronger case. And there's no trick here. These are perfect circular arcs. But they too only join with G1 continuity, which might be a little unexpected since we often think of circles as this ideal smooth shape. So what is going on here? First, let's look at the tangent directions. Now, they have quite a bit of overlap, so for clarity, let's use the normals instead. Now watch how they change as we move them across this path. You might notice they suddenly start and stop rotating at the joins, right where the circular arcs meet the flat segment. The angle of the tangent vector can illuminate this problem even more clearly. Notice how the angle is changing at a constant rate, then comes to a complete stop, and then it suddenly and immediately starts again. In fact, this is inherent to the nature of circles. Circles are the special case where the angle is changing at a constant rate, and flat lines is the special case where the angle doesn't change at all. So how do we even begin to analyze this to find out more about G2 continuity? We need a parameter-independent or speed-independent way to measure this. This is where we need to talk about curvature. Given a point on a curve, there's a circle that describes the curvature at that point. This is called the osculating circle. You can think of it as the circle that has the same curvature as the curve at that point. The radius of this circle is 1 divided by the curvature. Curvature can be calculated using the determinant between the velocity and the acceleration divided by the speed cubed. The determinant up there is a little confusing, but it's equivalent to what is commonly known as the 2D cross product, or the perpendicular dot product, or more accurately, it's the wedge product returning a bivector, but that's a topic for another day. So what does curvature look like across this spline? Let's travel along and see. There are a few interesting observations we can make. The first is that even though a point is only C0 continuous, it's possible to make the curvature continuous at that point. The second is that if a join is C1 continuous, that doesn't guarantee us curvature continuity either. And of course, it's especially bad in the middle where there's a huge jump in curvature. A very popular way to analyze curvature is using this handy tool known as a curvature comb. Let's again focus on a single join between curve A and B. The curvature cone grows larger the tighter the curve turns, and the more flat the curve is, curvature approaches 0. Now, we know that in order for us to have G1 continuity, we have to align the tangent points. In mathematical terms, this means P4 has to be a vector starting from P3 in the same direction as P2 to P3, scaled by some value. This means that we have 1 degree of freedom because this variable beta 1 can be any positive value. If it's 1, the tangents are mirrored, while any other value scales it. You might notice that the curvature comb isn't lining up, so this is still only G1 continuous. Deriving the math for this next step is significantly more complicated than for the parametric continuity, but long story short, we now constrain P5, also end up with another degree of freedom called beta 2. Now, watch what happens to the curvature comb as we apply this constraint. It's aligned. And we actually have 2 degrees of freedom to control this shape. No matter what values we set beta 1 and beta 2 to, we've successfully made this join G2 continuous. And of course, we can also move the control points and the constraint still holds. Now, the problem is again that even though we have a few more degrees of freedom, we have the same cascading problem of losing control over the entire spline. But did it solve our problem with shiny reflections? Well, yeah, looks like it does. It wasn't enough to have a continuous tangent direction across this join. We also needed curvature continuity to get rid of the seam in the reflection. It will even pass the harder dot pattern test. This is why G2 continuity is very important in industrial design, as anything shiny will respond very strongly to the shape of the curves.
It's not even the drive.
So G1 is when tangents are continuous. The curvature cone will also be aligned with itself across the normal of the curve. G2 is when curvature is continuous. The curvature cone is now continuous in and of itself. As you can see, it connects. Surfaces that are G2 or higher are sometimes called Class A surfaces. G3 is when the rate of change of curvature is continuous. The curvature cone will be, in and of itself, tangent continuous. Usually, you don't go higher than G3 as you get very diminishing returns in outcome, and the math becomes significantly more unwieldy for each step. So this is called geometric continuity. A more formal definition of geometric continuity is actually pretty tricky to come up with. But one that I like is that if you have two curves, A and B, they are Gn continuous if a function g of t exists, so that A of t and B of g of t are Cn continuous. It's kind of hard to wrap your head around it, but it effectively means that if we have full control over the parameter or speed at which we change the t value of one of the curves, if it's possible to make them line up into Cn continuity, the original curves are Gn continuous. It might seem like a lot to take in, but I can't stress enough just how important this is. Continuity is what justifies the existence of a whole host of splines. Let's summarize it all. C0 and G0 are equivalent. They are both positional continuity. It basically means your curves are simply connected in position. C1 is velocity continuity, as in the first derivative is continuous and the position is also continuous. In other words, it's not enough for the velocity to be continuous on its own, the previous derivatives have to be continuous as well. G1 is tangent continuity, which also requires that it has positional continuity, and the same pattern continues. C2 is acceleration continuity, which also implies velocity continuity, which also implies positional continuity. You get the idea. C3 is jolt continuity, G2 is curvature continuity, which again implies the previous ones. Finally, we have G3, which, in my opinion, is incorrectly called torsion continuity. It's also sometimes incorrectly called acceleration continuity. I don't know of a good name for this, unfortunately, but it's effectively referring to the rate of change of curvature. And so on. We can go on forever until C infinity and G infinity. Now, just like all the parametric continuities include all previous levels, and geometric continuity includes all their previous levels, there's another connection here. C1 continuity is also necessarily G1 continuous. If you remember, mirrored tangent points are also aligned. Effectively, G continuity is less strict than C continuity, so the C continuities actually imply their corresponding geometric continuity as well, but not the other way around. Generally. Before someone comments going, well, actually, I have to throw in a little caveat. This implication only applies if the curves are regular. Now, this is a bit of a math moment because, of course, regular has a particular meaning here that isn't the regular meaning of the word. A regular curve is one where the velocity is never zero. In other words, it never stands perfectly still. In fact, if we let this happen, a lot of our math we've been talking about breaks down completely. Both getting the tangent direction and calculating the curvature divides by zero if there's a point with zero speed. It's relatively hard to create a curve with this pathological behavior, but not impossible. For example, take this Bezier curve. If we place the tangent points at this exact location, we've created a point with zero speed. The curve is fully continuous, but watch what happens to the tangents. it instantaneously flips, which means it has a tangent discontinuity. This is called a cusp, and it's one of those rare exceptions where the curve is C infinity but only G0 continuous. We've only been talking about Bezier splines so far, but now that we're equipped with this extremely powerful tool to analyze continuity, I think it's time to visit the other splines in the extended universe. While the Bezier curve is useful, its points are pretty strange, are they not? They don't really refer to anything specific except the start and the end point. What if we can come up with another type of spline that makes more physical sense? What if instead of supplying 4 points, we set the start and end point as usual, but then we also set the start and end velocities? Another way of looking at it, we're supplying the boundary in position and the boundary in velocity, and then solving for the connection in between. This could be really useful when simulating physical objects, or even when interpolating movement data across a network. This means that we'll have a spline that automatically satisfies these constraints. It effectively auto-calculates the acceleration and jolt to make this curve. Coming up with this spline is actually pretty straightforward. As with any other math problem, let's list our known values and our constraints and solve from there. The start of the curve should be at p0, the end of the curve should be at p1, the velocity at the start should be v0, the velocity at the end should be v1. 4 equations means 4 unknown variables to solve for, which means we can use a cubic polynomial solving for a, b, c, and d. For example, one of them we can figure out immediately just by looking at it. If the equation should give us p0 when t equals 0, then a, b, and c are all multiplied by 0. This means that d has to be p0. And the same goes for the derivative when t equals 0. c has to be v0, and so on. I'll spare you all of the intermediate steps. Here's what we end up with, the matrix form of this spline. Now you might see the power of the matrix form. We now have the exact same setup where we have a powers of t matrix on the left, and a point matrix on the right, and then the characteristic matrix in the middle, giving us a kind of unique fingerprint for this spline. Just like before, multiplying the t matrix by the characteristic matrix gives us the basis function for each control point. This is what our new spline segment looks like. The cool thing about this one is that there's no more arbitrary tangent points. It's a spline that guarantees being at a specific place with a certain velocity at every control point, giving us a lot of control over the animation across the spline. If we analyze the first derivative, the velocity, you can see it matches at every point along the spline, and it's fully continuous. Though you might have noticed that the velocity itself looks like it changes pretty harshly, so let's look at the rate of change of the rate of change, acceleration. Here you can see that we have our first proper discontinuity. There's an instantaneous change of acceleration at each join. In other words, while this spline doesn't meet the criteria for C2 continuity, it is always C1. This type of spline where you supply explicit velocities at each point actually has a name. This is called a Hermite spline. Or, I mean, if you're French, you're probably dying inside right now. Technically, I think it's supposed to be pronounced ermite, but nobody says it like that, okay? So cut me some slack. Anyway, as you can see, the Hermite spline has explicit derivatives. And since both sides of each curve join share the same velocity, it is also by necessity C1 continuous. It's also worth noting, many Hermite splines out there allow for 2 velocities per join, one for the incoming curve and one for the outgoing curve, allowing you to make C0 joins as well. It's also interpolating, it's passing through every point and every velocity. Now, the Hermite spline is actually very closely related to the Bezier spline. Converting between the two is trivially easy. If you divide each velocity by 3 and add its origin, you get the Bezier tangent point. Flip that to the other side, and you now have the Bezier control points for the other side. This creates the exact same curve as the Hermite spline, but defined using Beziers instead. This also tells us that the Bezier tangent points correspond to exactly 1/3 of the velocity at the join. Next up is a spline we've been neglecting this whole time, which might be the most popular one out there. People just rarely call it a spline. The linear spline, simply drawing straight lines between each point. We might scoff at this shitty little basic spline, but it actually has a few superpowers. First, it's passing through every control point. No unnecessary bells and whistles, just straight to the point. No pun intended. Second, it's one of the few splines where arc length parameterization is easy. Arc length parameterization is when you want to interpolate a curve with constant speed, which is actually very complicated for almost all splines out there. Third, it's very cheap to evaluate. Here's the formula. It's just a lerp. But unfortunately, it's only ever C0 continuous. This property of passing through every point you supply is very useful though. So we might ask, is it possible to make a smoother spline that will pass through them all without having to specify derivatives? One method is to use a similar strategy as the Hermite spline, but instead of supplying the velocities ourselves, what if we calculate them based on neighboring points? We simply draw a vector between the neighboring points and use that as our velocity. And we repeat this process for every point. Look at the neighbors, form a vector, use that as our velocity, and so on. This is the curve we get. Now, it's not perfect. There are a few problems. First, it doesn't actually pass through the endpoints because they're missing one of their neighbors to calculate a velocity from. But we can sort of pretend we have an extra point. That's just the second adjacent point mirrored. This lets us extend the curve to the endpoints. And we do the same for the last point. Mirror the second last point around the last one to create this ghost point. The second thing we might notice is that the shape is kind of weird, isn't it? No offense to this spline, of course, but it's rather lumpy. For example, this part right here is very flat. And this part has a pretty sharp turn around flat sections. A good tool for analyzing this is the curvature cone. We can now clearly see the radical change in curvature across this spline. This sharp turn now has a very clear bump, and this flat section very clearly has curvature drop to almost zero, meaning it's linear or flat. Maybe it's a good idea to find some way to mitigate these sharp turns and flat sections. What if we apply a scale factor to all these velocities? Just scale them all down by some value. You can see the curve becomes much more relaxed, and as we continue, it actually approaches the linear spline. So with this scale parameter, we have a lot more control over the sharpness of the curve. Bringing back the curvature comb, you can see that with a low scale, the curvature is extreme at the joints and quickly flattens along most of the segments. Increase the scale, and the curve becomes much more relaxed, before getting a little bumpy again at a scale of 1. This type of spline with automatic tangents and a scale parameter and interpolating all points is called a cardinal spline. Here's what its matrix form looks like. As a side note, when you read up on cardinal splines online, they usually call this scale tension. But there's no consensus on how to apply this tension value. I found 3 different methods across the internet, so I'm just giving up and calling it scale, because I think this is the most computationally efficient way to define it anyway. The cardinal spline, however, is usually overshadowed by a closely related spline. When we set the scale to exactly 1/2, the spline looks unusually relaxed, doesn't it? There's no super flat sections and no super sharp turns where it doesn't feel justified. It's a very comfortable spline where you pass in some points and it just smoothly passes through without too much effort. This is one of the most popular splines in game development for this reason, and it's called the Catmull-Rom spline. It passes through every point except the endpoints that kind of need special handling. As for continuity, the curvature comb tells us it is G1 continuous. Let's also look at the parametric continuity. The first derivative is fully continuous, The second derivative, however, is not connected. You can see there's discontinuities here. So in the end, the Kaplan-Ram spline is C1 continuous. And there's no need to specify tangents, it just works. Of course, we can work out the matrix form of the Kaplan-Ram as well, letting us see its unique fingerprint and its basis functions. Let's actually take a closer look at these basis functions because they very clearly illustrate their relationship with these points. Remember, the basis functions say how much every control point should influence a given point in the curve. And so if we arrange them a little differently, it's now easier to tell how this represents the influence of a single point across 4 curve segments. To highlight this, let's focus on one point and its influence. The white section is where the point is pulling on the curve with a positive influence, while the red section is getting pushed away by the point as it has a negative influence. And this is how every control point behaves. Every point has its own wave like this, telling us how much it should influence each part of the spline. And this is what the full spectrum looks like. These influences then work together to carry a point across the spline. Each point has a peak, where it has 100% influence, guaranteeing that the point on the curve will be at the same location as the control point, and then its influence will drop off, letting the next point take over. A really neat thing is that we can analyze these basis functions on their continuity directly. We can tell that this one is continuous because all curves meet, and the ends are meeting with the x-axis line, and so C0 continuity is met. And what about the derivative of these basis functions? They are also continuous, so we're at least C1, which we would expect. The second derivative, however, has discontinuities. You can see how there are gaps in the graph, so we're still not C2 continuous. And isn't this a little frustrating? We've explored these new splines, and yet we're still stuck in C1 continuity land. Is there really no way to make a C2 an acceleration continuous spline? Well, the best way to test this is to try doing it yourself. In other words, fuck around and find out. Remember, the fingerprint of a cubic spline is the characteristic matrix in the middle. The challenge now is to find the 16 unknown values to make a C2 continuous spline. This means we need 16 equations to solve this, and let's see if we can make it work. The end of the first basis function has to be C2 continuous with the x-axis. That's 3 equations. The join between the first 2 basis functions also has to be C2, so 6 equations. We want a C2 join between the middle basis functions, 9 equations. C2 join between the last 2 basis functions, 12 equations. The start of the last basis function has to be C2 with the x-axis, 15 equations. We did it, right? Kinda, sort of. We've actually fit all of our constraints in, right? But we need one more constraint. Right now we have 1 degree of freedom. Luckily, we are actually missing one more thing. The basis functions all have to add up to 1 because they're used as a convex combination. 16 equations, 16 unknowns. This is now solvable. I will be skipping the steps involved in solving this system of 16 equations, but just trust me that it's possible. And so now, instead of the Kaplan-Ram basis functions, this is what our new basis functions look like. This looks really smooth. I think we've done it. This should be a cubic C2 continuous spline, where these are the values we end up with in our characteristic matrix. And now, the big question, what does this spline look like? Well, it looks like this. This might be a little surprising. This is the first time the curves don't actually meet at control points. The curves and their joins are completely outside of the control points. But what about continuity? This was, after all, our goal, to make a ridiculously smooth spline. If we look at the curvature comb, it seems G2 continuous. The comb is aligned and connected across the joints no matter what shape we use, so our geometric continuity is looking really good. We can also tell that it isn't G3 continuous since the curvature comb itself isn't tangent continuous. Remember when we tried to force the Bezier spline to be more continuous, we lost local control? Moving any one control point affected the rest of the spline under those constraints. But for this spline, we've still got local control over all the control points, and keeping continuity intact. So the geometric continuity of this spline is G2. How about parametric continuity? Well, we know it's at least C0, but did we manage to make it C2 continuous as well? Let's analyze it using animation this time. If we notice any sudden jumps, we have a discontinuity. The first derivative, in other words, the velocity vectors, are all looking very smooth. There are no sudden jumps as they pass the joints. So this spline is at least C1 continuous. Next up is acceleration. I like to think of acceleration vectors as pulling on the velocity vectors, and so I will draw them at the tip of each velocity vector. And let's see if we notice any sudden jumps. Again, the arrows never make any instantaneous change. This means we succeeded. We finally have a C2 continuous spline. Is it possible it's C3 continuous too? Well, that would be impossible since the geometric continuity would have to be at least G3, which it's not. But if you're curious, this is what the jolt vectors look like pulling on the acceleration vectors. As expected, this is where we have our first discontinuity. The jolt vectors jump as we pass across the joints. So, this soft little spline, while it's not interpolating, like, at all, it is actually C2 continuous. The reason this is possible is because we sacrifice the interpolating property in favor of the acceleration continuity. Of course, this spline has a name. It's called a B-spline, short for basis spline. Now that we've been looking at these for a while, it's time for a quiz. What spline is this? It might be hard to tell. It requires an unreasonably, actually impossibly keen eye to determine. But clearly it's a Bezier, right? You can practically see the control points just by looking at it. Or, wait, maybe it's a Hermite spline? Like you got the velocities and all? Or I guess it could be a Kepler-Rom passing through the points like that. No, wait, it's obviously a B-spline. Look at how smooth this shape is. Or what if it's a trajectory with a starting point, initial velocity, initial gravity, and a change of gravity? It's the path in space with a changing gravitational pull traversing for 1 second. That's what this is. Look, we can even do the matrix form for trajectories, which, personally, I think is super cool in and of itself, but that's a bit of a tangent. So what's happening here, trick question aside, is that all of them can generate this specific curve. Because all of these individual spline segments we've been talking about are actually very similar. First, they are all uniform. They presume you want to interpolate in a 0 to 1 range. Second, they are all cubic polynomials. They all fit this formula. So, if they can generate the same curve, what's even the point of different splines? So what I want you to keep in mind is that curves themselves are not splines. They are generated by splines. It's all about how multiple curves connect and how smoothly they are able to do so. What splines really describe is a transformation of control points. Given some control points, you use a spline to generate curves. If you swap out the spline, but keep the control points, you get different curves. I want you to think of splines as curve generators that make certain promises about continuity in the curve points, and how it treats the input control points. So it's not just about the end result, but the process you use to get there. You know, as they say, it's about the journey, not the destination. Except it's still a little bit about the destination too, but you know what I mean. I'm trying to make some sort of circular composite to summarize the family of splines we talked about today. The Bezier spline gives us a huge amount of control. It lets us create sharp corners, in other words, intentional tangent discontinuities, which is very useful when defining shapes like fonts or vector graphics, such as this heart. Hermite splines let us define explicit derivatives, guaranteeing it'll pass through its points with specific velocities. This is the most common spline for animation, and it's the basis for the animation curve editor in Unity, the game engine. For example, let's say we want to animate a jumping square. We can model its vertical position over time using a non-uniform 1D Hermite spline. Remember, non-uniform means the time interval between joins can vary, which is a little bit more complex than the uniform Hermite we talked about today. Anyhow, this lets us animate it. We can use another spline to make it do a little flip by changing its angle over time. Let's also animate its scale to make it all squishy and goopy. The camel ROM is the easiest way to just smooth a set of points when you wanted to automatically calculate the velocity, which is very useful for path smoothing, where passing through exact points can be important. The B-spline guarantees C2 continuity, and so it's the most popular spline in industrial design as it allows you to design curvature-sensitive reflective surfaces without losing local control. In addition, some animations are also acceleration sensitive, such as the movement of a camera, where instantaneous changes in acceleration look pretty jarring. The linear spline is not very smooth, but in some cases it either doesn't matter, or you have so many control points that it appears smooth in context. For example, if you need to draw a curve in a YouTube video about splines, the easiest and most practical solution is to simply sample the curve densely enough so that it looks smooth when drawing it as a set of lines. Now, we've only really scratched the surface of this enormous topic. In this video, we've mostly been talking about a specific subset, uniform cubic splines. All of these have counterparts of higher degrees. All of them also have the non-uniform variants, like the non-uniform Hermite spline we just used for the jumping box animation, where you have full control over not only the position and velocity at the control points, but also the time at which it should reach it. Or the non-uniform camel ROM, which has some interesting geometric properties when you set the knot intervals based on the distance between the points. And while the uniform B-spline we looked at earlier was useful in its own right, if we allow changing the time or knot values, we get the non-uniform B-spline. All the continuity promises of the B-spline are still intact, but each curve in the spline will now use unique basis functions based on the knot values. This, in turn, affects the shape of the spline too. There's an even more advanced variant called the non-uniform rational B-spline that lets you control the priority or weight of each control point, making the curves gravitate toward or away from specific control points. You might even have heard of this one before. It's more commonly known by its short name, NURBS. And remember the color gradient in the beginning of the video? Well, every color lives in the space of the RGB cube, where the dimensions are red, green, and blue. And so every color key in a gradient is a control point of a linear spline in color space. Then if we want to use this as a gradient map on an image, instead of using time as our input, we use the brightness of its pixels to sample the gradient. The output is then in full color based on our color spline. If we then move the control points, in other words, change the colors and time of our keys, the output changes along with it. As you can see, splines show up in many, perhaps unexpected places. The whole field goes much deeper than what we had time for today, but I hope you found this little exploration of math noodles interesting, and thank you all so much for watching. I want to give a huge shout out to Jazz Mickle for the audio and music that she made for this video. I want to thank Thor and Salad and Toast, our cats, that did a good job interrupting me recording the voiceover for this. This here is Salad. He is currently chasing Thor, which he is not allowed to do. So he's being a bad boy. Yeah. Bad boy. And then finally, I want to thank all of you, all of the Patreon supporters that have made this entire video possible. So thank you so much for supporting me. I also want to say that if you're not a supporter on Patreon, I think you should be if you like the work that I do. Patreon is also it's like the only platform that only takes 5% of the cut. Most other platforms take like 30% or 50%, which is absolutely ridiculous. And so Patreon is like a really, really good place to support work in general. So I would really recommend that. So this video took about a year to make, a little bit over a year, I think, from starting research to releasing it on YouTube. I think the scope of this video was way too big. I've kind of realized that splines is a very big topic. Like there are so many different avenues you can go. There are so many different things you can talk about. And I kept like adding more and more stuff to the video, and I always want to go like in depth about every topic I talk about. And it's impossible for this. I can't go too in depth about splines because then the video is going to be like 12 hours long if I want to cover everything that I researched. And so I think going forward, I realized that I should pick smaller topics or kind of plan from the beginning to like make them in chunks instead of planning for making a very long video. The initial goal for this video was to make a video that starts with lerp and ends at NURBS, which I guess I kind of did, except I didn't go into detail how NURBS work, because we didn't really talk about non-uniform splines. This project was incredibly big. I think I got like 3-4 months of work done, and then I burnt out completely and I couldn't work on it. I just couldn't. I started shutting down. I couldn't like focus a single moment on working on this.